Alright, today we're going to go over loop analysis, and here's a little comparison between the two. We have nodal analysis here, which we learned in the last two lessons, find voltages in the nodes, and loop analysis is finding the currents in the branches. So step one is to identify the loops you want to use, and ideally loops with the currents of interest. So say that we wanted to solve for I, okay? And notice that the direction is going into the node here. So it would be nice if we created a loop that was going into the node like this, okay? Now this loop could be arbitrary. It could be this way, or it could be this way. And either way is correct. You just need to make sure that you are consistent. And we're gonna do a step-by-step problem in that. So right now, I'm just gonna do it like this loop going this way. Okay, next step is to use KVL to write a loop equation, and it's like nodal analysis. Be consistent with the naming conventions. Make sure to account for all the currents inside a branch. So basically when you are doing a loop analysis against this resistor right here, you're going to notice that you have one current going down, I1, and then you have one current also going down because of our direction that we've chosen, I2. And so these guys are going to add up together, so it's going to go to R I1 plus I2. And now note, KVL is the sum of the voltages is equal to V1 plus V2, plus ... equals 0. And where in this case, each V is in terms of the currents, I1R plus I2R plus ... equals 0. And this is how we're able to find the I's, okay? And step 3 is to solve. So we're going to go ahead and do a practice problem. So here's a simple practice problem. And we have right here the currents in each branch. So we're trying to find the currents in each branch, okay? I'm going to remove those arrows so that it's clearer. Now, I am going to go ahead and do step 1. I'm going to choose an arbitrary loop, okay? I'm just going to say both of them are going counterclockwise. That's a terrible loop. I'm going to call this one I1 and this one I2, and loop 1 and loop 2, okay? So step 1 is to identify the loops. Step 2 is to apply KVL, okay? So we're going to go look at loop 1, and we're going to pick a starting spot. Let's just say we're going to start at ground. Why not? We can start here, we can start here, we can start here. We can start wherever we want in this loop, okay? And we're going to walk through it, applying Ohm's law, or, well, KVL. Both, like KVL uses Ohm's law, so in some aspects when we're doing an loop analysis. So we're going to walk through the 3 ohm resistor, and we're going to say, because we're writing in the form of R and then the sums of the currents in branch, right? That's what we explained earlier. So we're going to do R, which is 3 ohms. And I'm putting in parentheses here because notice that we have current I1 going up and we have current I2 going down. Now, my pro tip would be whichever loop that you're on, you're going to put that current first. So we're on loop 1, so we're going to put I1 first, and we're going to subtract I2 from it. Okay? Not equals yet. Now we're going to step through the 2 ohms right here, and we only have the I1 voltage current in it. Plus, now notice, we are going into this battery from the positive side. So we're going to go positive 5 equals 0. Okay. And so if we calculate this out, I'm going to distribute and we get this equation, 5i1 minus 3i2 equals negative 5. Now we're going to go ahead and solve for loop 2. So we're going to go up into the 10 volts from the negative side. So we're going to start with negative 10 plus 2 times I2 to get into voltage form, plus 3. Now, once again, we have 2 voltages going into this branch. I'm not voltages, currents going to this branch. I2 minus I1 equals 0. And we're going to get negative 3i1 plus 5i2 equals 10. Now the next step is to solve it. So we are going to put these two equations into a matrix. And then grabbing our calculator, we are going to solve for I1 and I2. And we are going to get I1 equals 5/16 and I2 equals 35/16. So I want you to notice something. These are positive values, okay? So what does it mean if you get positive values for current? So getting positive values for current means that the direction that you chose was correct, okay? What does that mean? So then that means that going counterclockwise on loop 1 is the actual physical way that this current is flowing. So I1 is flowing this way. And I2, likewise, is flowing this way into the node. Okay? Now, notice that it says to find the current in each branch. Okay? Well, we have not found the current in this branch yet. Okay? Let's call it I3. And I'm not going to draw a direction because it's going to confuse you. Now, how are we going to find the current in I3? Well, we're going to apply Kirchhoff's current law. Okay? And we're going to do that by adding up these guys. Okay, now notice something here. We've changed our coordinate system, but we're staying consistent because we are going to say that I2 is negative and I3 is going to be positive temporarily. Whatever we put into our nodal equation is going to reveal what we're actually doing. Okay, so we're going to say 5/16 minus 35/16 plus I3 equals 0. So we're going to do 5/16 minus 35/16. So we get I3 minus 15/8 equals 0. And we get I3 equals 15/8 amps. Okay, and don't forget to put your amps here. Now, what does that mean? That means that the legitimate physical interpretation of this I3 is going out of this node down. Okay? Okay. Now, technically, you could use the interpretation in here. However, there is a problem with that. And the problem is, which one do you choose? This one or this one? Now, I would just straight up use KCL to determine this because this is the surest fire way. This way, you could choose this one and you could get a different answer because you realize that the relationship between I1 and I2 was not arbitrary, right? I2 is going into the node, I1 is going out of the node in respects to KCL. Okay? And you could be lucky and you could choose this one, right? Which actually does correspond to the correct current going down that branch, which is 30/16 or 15/8. Long story short, I would not use these, okay? Because you could get confused. I get confused, okay? So why don't you just straight up use the rule that you were given, the law that you were given, okay? Call it at that node, even though you're doing loop analysis, to find that other branch, okay? Okay. Another thing that you could do is you could call this I3 and not have it split up, okay? In fact, but then you would have to introduce another loop, right? This huge loop, because you would have three variables and two unknowns. I mean, you'd have three variables and two equations, right? But I'm not going to do that because that is going to confuse you. It's going to confuse me. Now, I want to emphasize the idea of physical interpretation versus mathematical interpretation. Here we got all positive numbers, okay? But we want to make sure that we note that this guy is going to the left, okay? Left. And this guy, and you can say out of node. And this guy is going left into node. And this guy is going down out of node. Okay? Now I'm going to show you a scenario where this becomes absolutely crucial. Okay? We're going to do the exact same problem. Oh, excuse me. We're going to do the exact same problem, but we're going to change the direction of one of our loops. Okay? Because remember what I said? I said that the loops are arbitrary, and I'm going to prove that to you. So, we're going to say, instead of it both going counterclockwise, we're going to do one of them going clockwise. Okay? And the other one will go counterclockwise. Okay? I1 and I2, loop 2, loop 1. Okay? Let's go ahead and solve it. I'm not going to write down the steps. I'm just going to solve it, for you guys, just to prove a point. Okay. So we've got loop 1, and we've got -5 plus 2I1 plus 3. Now look at this right here. These two loops are going down the same branch together. So then that means they add up together this time. So we have I1 plus I2 as opposed to minus. Okay? Remember that. So we get 2I1 plus 3I1 plus 3I2 equals 5. And we get our nodal equation of 5I1 plus 3I2 equals 5. Now loop 2. Loop 2 is -10 plus 2. And plugging this into the equation, we get, okay, now look, this is negative. So then that means in this coordinate system that we had chosen, I1 is going into the node, and I2 is also going into the node, okay? But because it's negative, that means this rotation is wrong. It's not going clockwise, it's actually going the opposite way, okay? Now, there are two ways you can label this, okay? The first way is you can just say we have negative 5/16 amps going right into the node, and just double down on saying that it's going that way, because this negative current is telling you that you're going to add them up to go to the other side, right? What do I mean? So we're going into the node, right? A negative 5/16 is going into the node, negative 5/16 minus 35/16, because it's going into the node as well, plus I3 equals 0. Okay? And what are we going to get? We're going to get I3 equals negative 15/8. Okay? And likewise, it's saying that this guy's direction, this negative 15/8, is going out, but it's negative. Okay? So then that means that in reality, it's going this way. Okay? Does that make sense? Because this is extremely, extremely crucial. When I was first doing this, I did not understand that. And I would get these problems wrong all the time. I did the algebra and everything right, but I'd always get the directions wrong, and ultimately my solution was wrong. Okay? And this is the unfortunate scenario where you choose the wrong, thing. You choose the wrong direction, and that's okay. Okay? You just have to be consistent with you just need to notice what is important for your physical interpretation. Now, why does this matter? Okay? Because it matters because of your professor. If your professor says, find I, and they say this current is going this way, then you have to use the negative version. Okay? Why? You have to use the negative version because this professor is saying that this current is going this way. Okay? When in reality, the physicalness of the electrons are actually going this way, but your professor wants you to report this I, and this I is negative I1. Okay? I really hope that this helps. Nodal analysis is easier, loop analysis is easier algebraically, but it requires more thinking in terms of the direction. We didn't go as granular in nodal analysis because technically when you get a negative voltage, same thing. You just flip the battery to make it positive, okay? It's kind of like having negative versus positive cosines, right? Because it's an even function. This is the same case, okay? So, please rewatch this video if you need to. We are going to do a ton of examples in next lesson. So that video might come out a little bit later than I want it to, because I want to make sure that I do these problems correctly and originally. I'm also going to be covering more advanced examples of KVL, of nodal analysis and of loop analysis, including things called super meshes and super nodes. So stay tuned for the next video. I hope this helps. See you guys.